All right, good afternoon, everyone. Thanks for joining, and I hope everyone has been doing fine during this special time. Again, my name is Fang, and I'm an assistant professor in the computer science department at Portland State. And I consider myself a theoretician, and I'm particularly interested in the foundations of quantum computing and cryptography. So to explore what is possible and what is not, and also the interplay between these two subjects. So it's my pleasure to share some of my observations and experiences concerning cybersecurity in a quantum era. Yeah, and I want to thank Mark for organizing this event. Okay, so this talk is intended for a broad audience, but there are inevitably jargon and technical terms, and feel free to ask questions, and also leave a few minutes in the end for further discussion. Okay, all right. So I'll start with a problem which dates back to the Greek time, called the Diophantine equation. Okay, so we're given integers a, b, k, and we want to find integers x and y such that ax squared plus by squared equals k. So we want to solve this equation. And there's a special case, the Pell's equation, where we want to solve for x and y in this equation x squared minus dy squared equals 1. Okay, so despite these simple forms, this problem turned out to be really challenging to solve. And somewhat surprisingly, in retrospect, it turns out the majority of my research can actually be traced to Pell's equation. So let's get to it. Okay, so in modern algebraic number theory, mathematicians have figured out the solutions to a Pell's equation actually have a very nice geometric structure, which we call lattice. So there are points in the space which are regularly spaced in the space. So think of a grid or a pile of oranges, if that makes sense. So mathematically, an n-dimensional lattice is formed by taking n linearly independent vectors, which we call a basis, which is b1 to bn here, and then we take their integer linear combinations to form those lattice points. Okay, so let me stress that the coefficients need to be integers. So for example, in this picture, this is a 2D dimensional lattice. And these two vectors A and B, they form a basis that generates this lattice. And it's worth noting that the basis is not unique. For instance, there's another basis, C and D, which would generate the same lattice. So keep this in mind. We'll come back to lattices a little bit later. Okay, now let's look at a more familiar problem, which is also related to Pell's equation. So suppose I give you two integers, let's say 3 and 5. I guess it takes no time for you to figure out the product, which is 15. Okay. Now if I give you these two like uglier numbers, maybe it's hard to multiply them by heart, but we can just press a few buttons on a calculator and we can get the product. I guess the point is multiplication is easy. However, the reverse computation, the prime factorization problem, is way harder. Okay, so here we're given a large integer n, which is a product of two primes, and we want to find these two prime factors. Okay, and as the number grows, this problem becomes more and more difficult to solve. So think about it. The naive algorithm, which I think many of us might have implemented during our first introduction to programming class, is to enumerate all the integers from 1 to n. And in algorithm analysis, this is considered an exponential time algorithm, because to write down this big integer n, we need log n digits. And then this naive enumeration will take n steps, which is exponential in log n, the input size. Okay, and in fact, this prime factorization problem has been studied for a long time by many top minds, But still, the best algorithm so far, based on the number field sieve, takes exponential time. It's significantly better than the enumeration, but still it's exponential time. Well, so what does it do with Pell's equation? Roughly speaking, factoring is a special case of Pell's equation. Okay, and more precisely, we say that factoring reduces to Pell's equation. Namely, if we can solve Pell's equation, then we can also solve factoring efficiently. And this is denoted by this less than or equal sign to indicate that Pell's equation is as hard as factoring. Well, I suppose that's enough math. So let's get to cybersecurity. So many of the public key crypto systems which are deployed to secure our digital life is that they are actually built on factoring. So this is the famous RSA cipher suite, named after the three inventors, Ron Rivest, Adi Shamir, and Leonard Edelman. Okay, so they were awarded the Turing Award in 2002 for this remarkable achievement. So there excuse me, there are two basic primitives in public key crypto, which is public key encryption and digital signatures. So just a quick refresher. In public key encryption, a sender uses a public key to encode some message to obfuscated document so that only the designated receiver can decipher using the secret key, and no one else can read this document. So this provides secrecy. On the other hand, digital signature is concerned with integrity. Okay, so we want to make sure the message when receives is not modified by any attacker. So the sender would sign a message using his or her secret key, which the receiver can verify using the corresponding public key. So let me point out that, as the name suggests, the public keys, they can be made public. And in particular, the public key and the secret key, they don't have to be the same, and they're necessarily not the same here. But in contrast, in the long history, we only had what's called symmetric key cryptography, where the sender and receiver, they have to share the same secret key. So public key crypto was absolutely revolutionary when it came about in the late 70s. And later, as digital age moves forward, it becomes indispensable in securing the internet. So let's see some examples. So here are some protocols, cryptographic protocols, such as secure shell and HTTPS, which protects our information when we surf the web. And also this, sorry, not there, here we go. Also, these protocols further secure the services which we use in our everyday life, such as online shopping, cloud storage, and e-payments. Okay, so to reflect, it is no doubt how important that we need the RSA crypto system to be secure. And also we need the factor problem to remain a hard problem. Okay. Now, however, all of this will change when quantum computer comes. So in 1994, Peter Shor came up with a quantum algorithm that solves factoring efficiently on quantum computer. So as a result, RSA is broken, as well as the other crypto systems like the Diffie-Hellman key exchange, and all the protocols and services built on those will also be insecure. Okay, so let me stress that this break is fundamentally different from the other security breaches or vulnerabilities we might hear from time to time. So those breaches are typically due to incorrect or careless implementations, okay? And they rarely touch the RSA crypto system itself, let alone the factoring problem. But the quantum attack here completely cracks the factoring problem from the bottom. Okay, so I like to mention that the quantum factoring algorithm is usually credited to Peter Shor. But around the same time, there's another researcher, Alexei Kitaev, who independently found an algorithm, a quantum algorithm, which in fact solves a slightly more general problem. Kitaev, that was the early 90s, and Kitaev was in Russia then. So later on, they both made numerous contributions that shaped the field of quantum computing entirely. Okay, let me pause for a second. So now that we have seen the devastating threats to cybersecurity from quantum computing, we need to ask, what should we do? So this will be our next topic, which is post-quantum cryptography, the constructions which we hope would resist quantum attacks. And finally, if there's time, I might say a little bit more about quantum computing and some other further topics. Okay, let's get to post-quantum crypto. So factoring turns out to be easy on quantum computer, right? So naturally, we would like to have some other problems which better be hard for quantum computers to solve. Well, here come lattices that we introduced in the beginning of the talk. Just to recall, what is a lattice? So there are a bunch of discrete points generated by taking linear combinations of a bunch of vectors, a bunch of basis vectors, and the linear coefficients should be integers. Okay, so one computational problem in lattices is the closest vector problem, which says, I give you a target vector t, which is not in the lattice. I want you to find the nearest point in the lattice to this target t. For example, this one shown in the picture. Okay, and another problem is called the shortest vector problem, which can be seen as a special case of the closest vector problem, where the target is actually the origin. In other words, this is to determine the shortest distance between any pair of lattice points. Okay, so you might be wondering, this problem don't seem that difficult from this picture. For example, we might be able to tell that this vector A, okay, that seems to be the shortest one. Okay, well, this is because this basis AB I gave you is kind of a good one. They are already short and they're kind of orthogonal to each other. But imagine if I give you another basis, this CD basis. I guess it's less straightforward to figure out the shortest vector. And in fact, coming up with a good basis is essentially as hard as solving these problems. And more importantly, as the dimension grows, we will be facing a large search space that is difficult to navigate. And in fact, for both problems, the best known algorithms, either classical or quantum, take exponential time. So we have good reason to believe these are really hard problems, even for quantum computers. Okay, that's good. Now to give you some idea how lattices, or this lattice problem, could be a good fit for constructing crypto, let's look at this toy example, which is a digital signature scheme. Okay, so what we do here is we would generate a lattice together with a good basis, and this good basis will be the secret key. And we also produce a bad basis, which will be the public key. Okay, so again, a good basis means it's relatively short and it helps us to solve the closest vector problem. And the bad basis is kind of skewed and doesn't do anything good to solve the closest vector problem. Now, once we have this public key and secret key at hand, in order to sign a message, which we interpret as a target vector T, okay? So we're gonna use the good basis to find the closest vector V in the lattice, and that's gonna be our signature on this message T. And when the receiver receives the message T and the signature, which is the vector V, the receiver is just gonna verify that the signature V is indeed in the lattice, and then the distance between the message and the signature is indeed small. And this all can be done by the bad basis, which is the public key. Okay, so now the question is this secure? Well, apparently, in order to forge a signature, the attacker would need to figure out the closest vector to the message, right? But without knowing a good basis, this seems hard, because this is solving the closest vector problem. So this looks good intuitively, but unfortunately, a more careful analysis shows that as the attacker collects more and more message and signature pairs, it can learn some non-trivial information about the good basis. So in fact, this scheme is not secure. But nonetheless, I think the point here is I want to show that lattices, they do appear well suited to construct cryptography. And this is indeed the case. All right. So the good news is, inspired by those first generation proposals, lattice-based crypto has really taken off during the past decade. And modern constructions are based on an elegant problem called the learning with errors problem, or LWE in short. So this problem, this LWE problem, can actually be seen as a special case of the closed vector problem. So what this problem is about is, we're given a matrix A. Okay, so it's a random matrix, and the elements come from Z mod Q, and then we also sample a secret vector S together with a small error vector E, and we compute A times S plus E, which gives us the vector V. So once we are given A and V, we need to find the secret S. So let's look at this for a second. I think you can observe that without this error vector E, finding S from A multiplied with S, that's easy, right? Because that's just a system of linear equations, and we can solve by Gaussian elimination. So this additional random error E is really bringing this problem to another level. And that also explains the name, learning with errors. Okay, so it's been exactly 15 years since the invention of the learning with errors problem. And the community still believes it is hard for quantum computers to solve. So the learning with errors problem, LWE, is really versatile. And it enables constructing basic primitives such as hash functions or digital signatures, as well as the more advanced public encryption. And more surprisingly, in the last few years, cryptographers managed to realize some of their holy grails based on LWE, which no one knows how to do before using factoring. Okay, so you might have heard about fully homomorphic encryption. So it could, for example, allow you to store your data encrypted in Google Drive. And then Google can run some computation directly on the encrypted data without ever looking into your original data. And there are more fancy primitives like program obfuscation, which can be realized on LWE, plus some heuristics. Okay, so this really shows lattice crypto has been a success. But in the meantime, it's always a good idea to have a diverse portfolio, right? So here are a few other candidates for post-quantum cryptography. For example, you can rely on the hardness of decoding a random error correcting code, or solving systems of multivariate equations, and finding something called the isogenies among elliptic curves. So there's also a work specifically for designing signature schemes from cryptographic hash functions. And in fact, there's already enough faith in this direction, and a couple of RFCs have been drafted. So they could someday become the standard for future internet. Okay. All right. So these days, there's a much better appreciation of this issue. But it was a different story 10 years ago. There was quite some doubt, or sometimes people just shut off to this quantum security concerns or efforts. When I was looking for a faculty position in early 2016, I was really happy to see NIST's announcement that came just in time. They stated that they have a preliminary plan for transitioning to quantum-resistant algorithms. Okay, so when this is announced in public, it's serious. But how soon do we need to worry? Right? I guess that depends on 3 variables. So you have X, which is the time of your data that needs to be kept safe. And then there's the variable Y, which is the time to transit to a quantum safe infrastructure to update all the crypto systems, the crypto protocols. And then the variable Z, which is the time to build a full-scale quantum computer. Okay, so I want to quote the famous theorem due to Michele Mosca, which says, if X plus Y is bigger than Z, then you should worry. Well, this is self-evident and needs no further explanation. And usually, at this point, there will be the good old question, which asks, what is Z then, right? When can we have a quantum computer? But in my opinion, that's a valid question, but not a good one. There's actually a more pragmatic problem, which is often underestimated. You might have guessed, that is the time to migrate into post-quantum crypto, which takes time, a lot of time. And I'll elaborate on that in just a second. So by the way, I want to say that Mosca, he's one of the founders of the Institute for Quantum Computing at University of Waterloo in Canada, which is one of the most renowned quantum research institutes. So I worked with him when I was a postdoc there. I recall that basically almost every day, he would meet up with people from the government or from the banks and try to convey this issue to them. And I think he's been very successful. And Canada was a leading role these days in the effort of migrating to post-quantum crypto. All right, now let's talk about the effort at NIST, the National Institute of Standards and Technology. And they have an ongoing effort to standardize post-quantum crypto. And this will give us a sense, the time frame of the transition. So what NIST wants to do is basically to standardize schemes for both digital signatures and public key encryption, or practically the equivalent key encapsulation schemes. And this time, they're not looking for a single winner. So it's unlike the previous efforts, for example, for the standards for hash functions, the SHA family. This time they're looking for a few candidates, not just one. Okay, and then they will be looking at the security and efficiency, and also possibly some other application-specific features. All right, so I copied this table from one of their presentations last year. So here are a few key timestamps. So the project started in 2012. And after 5 years, there were 69 submissions and the round 1 review started. Okay, and then in January 2019, about 20-ish submissions were selected to the second round. And here's a recent update. Just last month in July, NIST announced the third round candidates. Okay, and they anticipate to finalize this process somewhere between 2022 and 2024. Okay, so keep in mind, so NIST standards don't imply that they will be deployed anytime soon, which could be magnitudes more complicated. Because after all, although NIST coordinates and communicates closely with the research community, but ultimately it's their call, right? But in contrast, think about the hundreds and thousands of entities on the internet, the hardware manufacturers, the service providers, and the internet task force. The list goes on. To give you a concrete example, you might have heard about MD5 and SHA-1, which are the early stages of the hash function standards. Okay, they still exist in many security protocols. Despite that almost 15 years ago, there's consensus and a strong recommendation that MD5 and SHA-1, they don't provide sufficient security. Okay, well, anyways, let's look at the positive side and congrats the third round winners. So there are 4 candidates for public key encryption. 3 of them are lattice-based and 1 is code-based. Okay, and then there are 3 candidates for digital signatures and 2 are lattice-based and the other one is based on multivariate equations. So just to show you this update. And if you're interested, I highly encourage you to sign up for their discussion forum. They're very insightful discussions, and it's intriguing to just see day by day how the schemes get broken or get improved by a collective effort. Okay. All right, so I want to point out that although this is already a very slow process, the post-quantum candidates are still relatively new. And even more so is our experience with possible quantum attacks. So I want to share with you a successful quantum attack on some lattice-based crypto systems. Okay, so the story begins with some practical concerns for efficiency. That matters a lot in practice. So cryptographers, they sometimes use variants on the learning with errors problem, and especially they pick some really structured lattices. For instance, there's a problem called short PIP, the short principal ideal problem, which basically asks you to find a short generator of a very special lattice. And there are various crypto systems built on it. Okay. However, this turns out to be a bad idea. Okay. So people found that, in fact, once you have a generator, then you can effectively reduce the size to find a short generator. So that means the difficulty solely relies on finding an arbitrary generator So this is the principal ideal problem, PIP. And with my collaborators, we came up with an efficient quantum algorithm. And you can see as a result, this would solve the short PIP and also break the cryptosystems based on it. Okay, so I think the message here is it's just too soon to be certain, and we need more cryptanalysis from a lot more people. And here's another issue, another threat to security, which is possibly as profound, but it is often overlooked. So far, we've been concerned mainly with the hardness of the problems that we build crypto on. But that's not the whole story, okay? So modern cryptography relies on a formal methodology. And this distinguishes it from the practice of crypto in a long history of human beings, which is largely an art. So this picture shows the two Turing awardees, Shafi Goldwasser and Silvio Micali, who pioneered the revolution of modern cryptography from based on a formal approach starting the early 80s. Okay, so roughly, to talk about security, we first need to define precisely what security means in a security model. For example, what is the syntax of encryption? What kind of attackers do we consider? Right? And once we have a formal security definition, then we'll come up with a formal security analysis to establish the security. And this is typically a proof showing that the security definition can be satisfied, assuming the underlying problem is hard. Or equivalently, taking the contrapositive, we need to show if assuming there is an attacker that can break the crypto system, then one would be able to solve the hard problem, which gives us a contradiction. Okay, so both of these two components could fail in the presence of quantum attackers. There are unique quantum attacks which are not covered by the classical security model, right? And also, some of the security proofs, they may become inapplicable against quantum attacks. So the bottom line is, just because we're using a problem presumed to be hard against quantum computer, that doesn't mean the crypto system is immediately secure. Okay. So one of my major research efforts is actually to develop a formal framework for quantum provable security. If you're interested, you can check out some of my talks and publications to find more. Okay, how am I doing on time? Okay, very good.
Oh, you got plenty of time. Yeah.
Okay, so I think we have time to go over the last section. And consider this as the bonus content. Okay, so I suppose many of you already have some basic idea about a quantum computer. Right, so I'll just give a brief intro and possibly from a different perspective. So the first question is, what is a quantum computer? Right? I guess, if you Google an image a few years ago, you probably hit this weird one on the left. And these days, you'll be more likely to find out something more reasonable. Right? So on the right-hand side, that's a picture, I think, from IBM. So that's solid. Okay, so back to the basics of quantum computing. Well, we all know the basic unit of classical information is a bit, right? 0 or 1, which can be identified with either sides of a coin, heads or tails. And also the bit can, in general, be randomized. So namely, it can be the outcome of a coin flip. So let's say it lands on heads with probability p0, and it lands on tails. Sorry, this is a typo. I have both heads. One should be identified with tails. So let's say it lands on heads with probability p0 and lands on tails with probability p1. So by probability theory, p0 and p1, they need to be non-active and less than 1. And their sum has to be 1. Right? But quantum physics tells us that our world actually runs with the extended probability theory, where p0 and p1, which we call amplitudes in this context, they can be negative or even complex numbers. And the only condition is that their absolute value squared sum up to 1. So if you've seen some real analysis, this just means it's normalized under the L2 norm rather than the L1 norm as in classical probability theory. So this leads us to a quantum bit, or qubit in short, which physicists call a quantum superposition of 0 and 1, or heads and tails. So this expression down here, 1 over square root 2 ket heads plus 1 over square root 2 ket tails, this actually describes the state of the famous Schrodinger's cat, which is in a quantum superposition of alive and dead. Okay, now, once we have the bits, right, a classical computer is basically a circuit consisting of this basic Boolean gates, and, or, not, etc. Similarly, there are quantum gates which can operate on qubits, and they can be composed to a quantum circuit that computes something interesting. So this gives us a quantum computer. But what does it buy us? Well, for starters, it seems infeasible to simulate a quantum circuit by a classical one, because even just to describe an n-qubit quantum state, that would need 2 to the n classical bits. And indeed, we have examples, such as factoring, where a quantum computer can solve much faster. Okay, so I'd like to point out that sometimes people attribute the quantum speed up to massive parallelism, but that's not accurate, and we should try to avoid this misconception. All right, I think that's my introduction to quantum computing in maybe 3 minutes. Now let's switch gear, okay? So the threats we discussed earlier for the most part of the talk assume the attackers have a quantum computer available. But of course, there's no reason prohibiting the honest users also to take advantage of quantum computing, right? In particular, they can design crypto schemes where they exchange and process quantum information. And a notable example is the quantum key distribution, where 2 users, they agree on a secret key by exchanging quantum data, quantum information. Right? And this communication is public. And in the end, they can agree on a secret key. So as we can observe that classically, if all the messages exchanged are classical, a eavesdropper could, in principle, transcribe all the messages and then, take it back, sit in his or her office and figure out the key. This may take a lot of time, but it's possible in principle. But in contrast, quantum key distribution is secure regardless how much computation the attacker, the eavesdropper, is willing to invest. And this is roughly because the quantum information exchanged, since there are unknown states to the eavesdropper, and there's the quantum non-cloning theorem saying an unknown state cannot be copied. And any attempt from the eavesdropper would disturb it in some way, and this could be detected by the honest users. And this is like the rough reason why QKD can provide security against computationally unbounded eavesdroppers. Okay, so QKD provides a quantum solution to a classical problem. But we can also imagine one step further. Someday, communications, we might be communicating quantum information, okay? And we would need to encrypt and authenticate quantum data. So we'll need some cryptographic tools for that. So all this can be called quantum cryptography. And it's worth pointing out that the technology for quantum cryptography is actually relatively more ready than a full-scale quantum computer. So this picture shows a QKD box. That's a commercial product you can purchase. I don't recall how much it is. It's not too bad actually. You can basically buy 2 boxes, place them in the 2 corners of your playground or your backyard, and then run a QKD experiment. Okay, so indeed, so parallel to building a full-scale universal quantum computer, there's also a vision of augmenting our present internet with quantum communication and quantum cryptography. And there have been considerable efforts across the world from the European Union, China, and Japan, and Canada. So US was kind of late in this game, but there seems determination to catch up. So seems like they're willing to put in a lot of funds in the next few years. Okay, all right. I hope you've got some interesting information about the quantum threats to cryptography and cybersecurity in general. And then there's also ongoing effort to design the next generation of quantum safe cryptography, including both post-quantum crypto and this alternative approach of quantum cryptography. And this is going to be a slow process, but and we need more people to work on it, to devote more efforts to put their security on a firm ground. And finally, I think I would list some pointers for people who want to learn more. For instance, I didn't talk about what would happen to symmetric key crypto at all, but here's your treat offline. All right, I think I'll stop here, and I'm happy to take any questions and bring any further discussions alive.
Thank you so much, Fang. That was fantastic. There was one question from Arland. When doing the math, do you use real space or the reciprocal lattice Fourier space?
When doing the math, do you use real space or reciprocal lattice? That's a very good question. Well, depending on what problem you're asking, for example, the closed vector problem, we're usually just talking about the principal, the principal lattice. Okay, but there are some algorithms, you can imagine in your algorithm, sometimes it's helpful to figure out something about the dual lattice, which might be helpful for you to solve the problem in the principal lattice.
Thank you. So Barry Bird just asked a question about, do you see it in the chat there?
Yeah, I'm looking at it.
Yeah, about NP complete and exponential time and such.
Okay, I'll read this question out and then I can process it. Are the following assertions correct? Factoring by classical methods takes exponential time. Shor's algorithm solves factoring in less than exponential time. NP problems are probably not p-time reducible to factor. So reductions using quantum computing probably don't help solve NP problem in p-time. Okay, very good question. So for people who are not familiar with the notions P and NP, P basically means the collection of problems which can be solved efficiently, meaning polynomial time on a classical computer. Right? And NP is the set of problems which we can verify efficiently. We may or may not be able to solve them, but once somebody gives you an answer, you can verify efficiently. So clearly, P is a subset of NP. And the current belief for factoring, it's hard to say. Like, it depends on who you ask. Some people think factoring will be, like, we will be able to find a classical polynomial time algorithm for factoring. But so far, I think the common belief is factoring is not in P. So it's hard to solve in polynomial time by a classical computer. Okay, I guess that's just kind of reiterating the first part of your question statement. And then the second part, you're asking, NP problems are probably not P time, right? So reductions using quantum computing probably don't help solve NP problems in P time. Yeah, that's again an open question. We don't have a definite answer. And although quantum computers have proven this extraordinary power for solving some of the problems not believed to be in P, but in the meantime, there's evidence saying a quantum computer probably cannot solve NP complete problem either. So it's more, so if we draw this Venn diagram, think about the circle containing NP problems and the circle containing problems that can be solved efficiently by a quantum computer. They're mostly intersecting, but there's no strict containment in either way. I think that's the current understanding by most people.
That was a really good question, because it shows that quantum computing has highlighted that not only do we not know a lot of things, we don't even know what we don't know.
Yeah, I think that's a good summary.
So Arland from before has a follow-up question. How would you get into quantum cryptography?
Okay, good question. How do you get into quantum crypto? I think, I would recommend starting with QKD, which is, there are lots of tutorials around, since QKD actually was first proposed in the 80s. Yeah, actually, it's kind of a coincidence. It's about the same time as the start of modern cryptography, of public key cryptography. But somehow people took the route of public key crypto and this modern crypto. But QKD didn't get enough attention in the early years. But now it seems like a very good supplement. So I think to learn about QKD, I would recommend you to check out the website of IQC, the Institute for Quantum Computing at University of Waterloo. I think they have lots of video tutorials available. Or if you want something more specific, feel free to shoot me an email. I can send you some pointers.
So Barry has a follow-up question to the PNP question from before. So if there is a classical solution to factoring in polynomial time, then RSA can be broken in principle without quantum computing?
Well, that's totally possible. Although we don't want, well, I guess most people don't like that way, but it hasn't been ruled out yet. So the best we know is despite all this effort, so far we don't know how to solve it efficiently on classical computer, but it might happen next day or next week or next year, who knows?
So the next question is from Safe. Would you consider quantum cryptography to be the ultimate solution with post-quantum crypto as an intermediate one? The fact that there are currently no solutions to the problems used in post-quantum doesn't mean that they will never be solved one day.
Yeah, that's a good question. So I guess just to clarify a little bit, post-quantum crypto basically means the scheme itself is still classical, meaning it can be implemented on a classical computer. On the other hand, quantum cryptography means the ANSI users, in order to run this quantum crypto scheme, they have to have some quantum capability, right? And I would say, this is my personal opinion. I wouldn't consider quantum cryptography to be the ultimate solution, and post-quantum crypto to be like the makeshift for now. I really think these two approaches will be coexisting. They will supplement each other. And I think the most likely scenario might be, because of the nice features of QKD, we can rely on QKD to distribute secret keys, and then we rely on post-quantum crypto to do the actual, like the hard work. Yeah, that's my take on this.
Thank you, and I think you've actually just answered their follow-up question already. Is there one more question that anyone would like to ask? Good, from Benjamin Cordier. Are there practical challenges to implementing interactive protocols based on post-quantum crypto? I'm thinking of the Meetup protocol for classical verification of a quantum computation.
You're really advanced. So Meetup's protocol, this is really remarkable. So she, well, I can't help talk about this story. So she was a PhD at UC Berkeley, and she, during her first 6 or 7 years, she didn't publish anything. And then the last year, she made this like surprising contribution where she constructed an interactive protocol where a classical computer can verify a quantum computer. So for example, if I jump out and say and claim I have a quantum computer in my office, would you believe it? Well, but Meetup's protocol gives us is a way to check on me, to verify whether I'm just whether I really have one. So to implement this protocol, in fact, the verifier, the classical user, doesn't need to have any quantum computing capability. So I don't see any difficulty implementing this protocol. It's just the server side. Whoever claims that he or she has a quantum computer needs to really do something quantum to pass this test.
Good, and I think for the last question we'll take from Paul. Post-quantum cryptography and quantum computer threats are only known in the developed world. How do we create awareness in the less developed world about the threat? Hackers always try the weakest link. If we do not have the whole world aware and ready, how does the whole world stay connected?
Yeah, that's an excellent question. Indeed. Well, as I mentioned in my talk, earlier in the talk, a few years ago, people didn't take this very seriously, or they just, this is something new. Then, as human beings, we're always lazy. We wouldn't want to take any challenges which are not familiar to us. So a few years ago, even not just within US, all the developed countries, US, Canada, not just the broader audience, like the general public, even researchers, like you will find yourself kind of isolated in those top crypto conferences. Like people talk about classical crypto, there are fancy constructions of all this, fully homomorphic encryption or whatever. And if you're given presentation on something about post-quantum crypto, how to prove security, how to design a new like quantum crypto protocol, you don't get a big audience. So I don't have any concrete kind of solutions, but I think we did. I mean, this is an excellent question. I guess it takes time. Maybe, it's just we just need to spread the word, right? Now, today you heard about this message, then you can talk to your friends, talk to your people around you. And sooner or later, there will be more and more awareness. And hopefully, something can be done.
Super. Thank you so much, Fang, and thank all of you. Again, I recorded this, and so I'll place it on YouTube tonight. I'll see you all again in 2 weeks.
All right. Thanks, everybody, and take care.